And a question was also asked about number 13 on the 10-3 worksheet, so let's take a look at this one. Okay, it says that your math teacher, very handsome, very witty, you know him, he draws a regular hexagon with a circle circumscribed around it. Oh, I really wish I had the tools on my normal smartboard, but for now I'm just going to have to wing this, guys. So we're drawing a regular hexagon, which is 6 sides that are all congruent, and all your angles are congruent as well, and then a circle is circumscribed around it. And this is where it's going to look really bad, guys, but I'm supposed to draw a circle that passes through all 6 of those points. So not my best work, but it'll work for now. They tell us here that the radius of that circle is 5 meters. Now, a circle has an infinite number of radii. We could draw them anywhere we want, but I usually draw them down here to the bottom right-hand corner, and this is where my drawing is bad. That one point that I'm drawing right now should be both a point that's located at a vertex of the hexagon and also a point located on the circle. And they tell us that that radius right there has a length of 5 meters in blue. And the question now is, to the nearest tenth, what's the area of the hexagon? Okay, well, the fact that it's a regular hexagon means that once again we can use our formula here that we're using all over in 10.3. That area of a regular polygon is 1/2 times the perimeter times the apothem. The tricky thing about this problem is, as I try to move on into step 2, we've got problems. We don't know the perimeter of the hexagon, nor do we know the length of the apothem. So we've got a lot that we have to worry about right here. The first thing we probably ought to do in just about every one of these cases is draw the apothem in, and I always like to draw mine going down. It doesn't have to be that way, but that's the way I like to do it to be consistent, and the apothem is always perpendicular to the side that you draw it to. Okay, let's have a quick conversation then about theta, the measure of your central angle. The formula we've been using lately is that theta is always going to be 360 degrees divided by n. When n is the number of sides, we need to remember that in a hexagon, that means that n is 6. So theta in this problem is going to be 360 divided by 6, which is going to get you 60 degrees for the measure of a central angle. This angle right here between the apothem and the radius is always going to be half of that angle right over there. So that tells us, guys, that this is a 30-degree angle located right there between the apothem and the radius. So a 90-degree angle and a 30-degree angle tells us that this one has to be 60 degrees. So what really shouldn't be surprising you right now is the idea that we are dealing with, if I were to redraw this a little bit bigger down on the bottom, there's our apothem here, here's our radius, and that this angle that we form in every regular hexagon is always going to be a 30, 60, 90 triangle standing up. Now, in terms of what we know about this triangle here, we know that the radius, which is our hypotenuse, has a length of 5 meters, but we've got to figure out both A, which is the length of the apothem over here, and also this piece down here on the bottom, which we're going to need in order to get the perimeter. Okay, so in a 30, 60, 90, the key side is always going to be the short leg, which is right down here on the bottom. To go from short leg to hypotenuse, we always multiply by 2. So to go backwards from hypotenuse to short leg, we're going to divide by 2. 5 meters divided by 2 is going to get us 2.5 meters for the length of this piece down on the bottom. Now to come up with the length of the apothem, to go from short leg to long leg up here, we always multiply by the square root of 3. So this apothem here is going to be 2.5 times the square root of 3 meters, and there's nothing else we can do to clean that up. So that actually tells us the length of A here. 2.5 multiplied by the square root of 3 is the length of our apothem. Let's go back and let's talk about perimeter now, guys. And the perimeter is the sum of all 6 sides of that hexagon. Well, we found that this piece right down here, which is right here in the diagram, was 2.5 meters. This one next to it would be 2.5 as well. So if we add together those 2.5s, one side of that hexagon is going to be 5 meters. There are 1, 2, 3, 4, 5, 6 of those 5 meter sides within this hexagon. So the 6 times 5 is going to give us a perimeter of 30 meters. By the way, this is something, I don't want to call it a coincidence here, but in every hexagon that you're ever dealing with, when you draw 2 radii right next to each other, like these 2 sides in black, the length of those radii are always going to be the same as the length of a side length. Only in a hexagon, this triangle is always equilateral. That doesn't happen in any other figure, but in a hexagon, that's always going to be the case, that all three of those sides are the same length. Anyway, back to the problem at hand. We did the hard work, guys. We found the perimeter, we found the apothem, so let's go ahead and put it all together right here. Multiplying the 1/2 times the 30 is 15. The 15 multiplied by the 2.5 root 3 is going to get us an exact answer of 37.5 times the square root of 3. Everything was in meters here, so the area is going to be square meters. This is the exact answer, but again, the directions here on number 13 asked for the area of the hexagon to the nearest tenth. So if we wanted to do that, I'd go to my calculator and take 37.5 and multiply that by the square root of 3 to get an answer of 60, nope, that would actually round up, to, oh, now I broke it, hang on. Go back right there, that's the wrong problem. Okay, I think I lost that problem altogether. Anyway, should have been 65.0, everybody, would have been the answer to that problem there for problem number 13.